Drone, tiny flying machines that are now powering an industry worth more than $73 billion.
So how are they actually made? Behind that compact shell lies a complex system of technology.
Sensors that keep the aircraft stable even in strong winds, and ultra-small electronic circuit boards processing every control command in an instant. Join the Factorin as we step inside a modern drone factory to explore how raw materials, electronic components, and hundreds of precision engineering steps come together to create an intelligent flying machine capable of lifting off into the sky. Drones can create massive light shows in the sky. At festivals and major events, thousands of drones fly in synchronized formations, like glowing flocks of birds, arranging themselves into giant images against the night sky. Every movement is programmed with centimeter-level precision, turning the sky into a living stage of technology. In just a few minutes, they can draw logos, symbols, or even moving stories in the air. A form of technological fireworks for the modern era. Yet those same small flying machines are also playing a very different role in today's world. On the battlefield, military drones have become an important strategic tool. They can fly deep into dangerous areas to conduct reconnaissance, track targets, or carry out precision strike missions. The first stage in the production of a drone begins in the design room, where engineers build the entire structure of the aircraft using CAD software and aerodynamic simulation systems. On computer screens, the drone's 3D model is continuously rotated and analyzed to determine the exact dimensions of the body, the position of the motors, and the spacing between the arms that hold the propellers. These simulations allow engineers to predict how air will flow around the drone's body when it flies at speeds of around 40 miles per hour, helping them refine the shape of the frame to reduce drag and improve stability. Alongside the design process is the selection of materials for the drone's frame. Manufacturers typically use carbon fiber reinforced polymer, a composite material widely used in the aerospace industry, because it combines very low weight with high structural strength. Thanks to this material, a complete drone frame often weighs only about 3.5 ounces, yet it is strong enough to withstand the constant vibrations produced by motors spinning at tens of thousands of revolutions per minute. The result is a compact but durable frame capable of keeping the entire system, including the camera, battery, and circuit board, stable throughout the flight. After the composite materials have been prepared, the process of shaping the drone body begins using multi-axis CNC machining centers. Blocks of engineering polycarbonate or sheets of carbon fiber are secured onto the machine table, where high-speed cutting tools begin removing material layer by layer in extremely thin passes. In drone manufacturing, CNC machines often operate with spindle speeds reaching around 20,000 revolutions per minute. This level of precision ensures that the drone's 4 motor arms are perfectly aligned, because even a very small deviation can cause vibrations when the propellers spin at high speed. Inside a modern factory, multiple CNC centers operate continuously along the same production line. A single machine can finish machining half of a drone frame in about 3 to 5 minutes. And when several machines run together, the line can produce hundreds of frames every hour. The cutting tools follow pre-programmed toolpaths, holes, carving channels for electrical wiring, and machining the surfaces where cameras or sensors will later be installed. This automated process allows every frame to be produced with extremely consistent dimensions. Once the CNC machining is complete, some composite parts are briefly heated in an autoclave to strengthen the bonding of the material layers. The components are then removed and inspected using a laser measurement system to verify their dimensions before moving on to the next stage of production. The motor is the component that generates the lifting force for the entire drone, which is why the production of a brushless motor is carried out with extremely high precision. In modern drone manufacturing plants, the motor production line is usually separated into a dedicated area, where mechanical and electronic components are machined and assembled step by step. The process begins with the stator, the stationary core of the motor. Ultra-thin electrical steel sheets are stamped, hitting high-speed presses to form ring-shaped cores with multiple slots around the circumference. Each sheet is only about 0.02 inches thick, and dozens of these layers are stacked together to form a complete stator block. This laminated structure helps reduce magnetic losses when the motor operates at high rotational speeds. Once the stator core is formed, pure copper wire is wound around the slots using automatic coil winding machines. These copper wires are extremely thin, with some types measuring only about 0.01 inches in diameter. Yet they must be wrapped hundreds of times in a precise. The winding machines operate fully automatically, rotating the stator while maintaining constant tension on the copper wire to prevent overlap or breakage during production. At the same time, the rotor of the motor is also manufactured. The rotor is typically a small cylindrical metal housing fitted with powerful neodymium magnets inside. Robotic arms position these magnets precisely and secure them using heat-resistant industrial adhesives. Accuracy at this stage is critical because a drone rotor can spin at speeds of up to 40,000 revolutions per minute. The two components are assembled into a finished motor. Technicians or robotic systems install the central shaft, miniature bearings, and retaining rings to ensure the rotor spins smoothly around the stator. A complete drone brushless motor typically measures about 1 inch in diameter, yet it can generate enough rotational force to lift an entire drone into the air. Before leaving the production line, each motor is connected to a testing device that measures rotational speed, electrical current, and vibration levels to ensure stable operation at very high speeds. After the motors have been manufactured, one of the most critical components of a drone begins production: the electronic circuit board, also known as the PCB, which controls the entire flight operation of the device. In modern drone factories, PCB assembly lines usually operate inside clean room environments to prevent dust or static electricity from damaging the extremely small electronic components. The process starts with printed circuit boards that already contain etched copper pathways for electrical signals. These boards are fed into an SMT production line, short for surface mount technology, where high-speed robots begin placing electronic components onto the surface of the board. Pick-and-place machines use vacuum nozzles to lift tiny components from feeder trays and position them precisely on the PCB according to a programmed layout. In a modern production line, these machines can place more than 20,000 components per hour, including microprocessor, motor control. Once all the components are placed, the PCB passes through a reflow oven, a multi-zone industrial soldering furnace. Temperatures inside the oven can reach around 460 degrees Fahrenheit, hot enough to melt the solder paste beneath the components. As the board moves along the conveyor through the oven, the molten solder bonds the components. Leads to the copper traces on the PCB, forming strong and reliable electrical connections. After soldering, the circuit boards move through an automated optical inspection system,
equipped with high-resolution cameras. This system compares the position of every component
against the original design to detect issues such as misaligned chips, missing components, or defective solder joints. Working together to process flight data, stabilize the drone in the air, and coordinate the operation of all the motors simultaneously. After the drone frame and the electronic circuit board have been completed in the previous stages, the assembly process begins, transforming separate components into a fully functional drone. The assembly line is usually divided into several sequential workstations, where each technician is responsible for a specific task. The drone frame is secured on an assembly fixture that keeps the four arms perfectly aligned. The remaining components can be installed quickly and accurately. The first step is installing the brushless motors onto the 4 arms of the frame. Each motor is fixed in place using small steel screws, while the motor wires are routed into the central body to connect with the control system. During installation, technicians carefully align the motor shafts to ensure they remain perfectly straight, since even a small misalignment could affect the drone's balance during flight. Next, the flight control board is mounted in the center of the drone using rubber vibration dampers.
These dampers absorb vibrations from the motors and protect the sensitive electronic components on the board.
Wires from the motors, sensors, and power system are then connected to the appropriate ports on the controller. Once the control system is secured, additional modules are integrated, including the stabilized camera, obstacle detection sensors, and the GPS module. Once the control system is secured, additional modules are integrated, including the stabilized camera, obstacle detection sensors, and the GPS module. A typical drone battery has a capacity of about 4,000 milliamp hours, providing enough energy to power the motors, sensors, and onboard electronics. After the drone's hardware has been fully assembled, the device moves to the stage of programming and calibrating the flight software. At this station, technicians connect the drone to a computer through a data port to install the control firmware. The first step is loading the flight control program into the flight controller. This software is configured to manage multiple onboard systems,
including GPS positioning, flight stabilization, and motor speed control.
Once installed, the firmware allows the controller to process data from sensors and send commands to the motors in real time during flight.
After the firmware installation is complete, the drone goes through a sensor calibration process.
Each sensor must be carefully adjusted to ensure accurate orientation and motion detection. The GPS system is also tested during this stage to confirm that the drone can determine its position with an accuracy of about 3 feet. This calibration ensures that the drone can maintain stable flight, hold its position in the air, and navigate precisely when it is later operated by the user. After the flight software has been programmed and the sensors have been calibrated, the drone moves to the flight testing stage, where the entire system is evaluated under real operating conditions. In modern drone manufacturing facilities, this step usually takes place in a dedicated testing area, where engineers can monitor the drone's performance through data screens and measurement systems. Before the test flight begins, the drone is placed on a testing platform, where the motors are powered on and the control response is checked. Once the system confirms that all signals are stable, the drone takes off within the testing zone. In a standard test, the drone typically climbs to a height of about 50 feet to evaluate its balance and control response. During the test, engineers perform a series of maneuvers such as ascending, descending, changing direction, and rotating in place to assess the drone's stability. Throughout the flight, onboard computers record data from the sensors, motors, and navigation system
to verify that each component performs according to design specifications.
Many commercial drones can reach max speeds of around 40 miles per hour, which makes this stage critical for confirming.
After successfully passing all flight tests, the drone moves to the packaging stage, the final step before the product leaves the factory. Each drone is placed inside a custom-molded foam tray, a material designed to hold the device firmly in place and absorb shocks during transportation. Alongside the drone, accessories such as the remote controller, spare battery, charger, and replacement propellers are arranged in separate compartments. A complete commercial drone package typically weighs around 2 to 3 pounds when all accessories are included. Once packed, the individual boxes are transferred to a larger packing area where multiple units are placed into shipping cartons. These cartons are then stacked onto pallets, allowing dozens of drones to be prepared for large-scale transportation. From there, the products are shipped to distribution centers around the world, where they will eventually reach retailers and customers. From raw material sheets and tiny electronic components to modern production lines, the journey of building a drone is hundreds of different parts must be carefully designed, machined, and assembled with high accuracy to create a compact flying machine.
Capable of lifting off and maintaining stable flight in the sky.
If you found the drone manufacturing journey interesting, make sure to like the video and share your thoughts in the comments below. And don't forget to subscribe to the channel so you won't miss our upcoming videos.